How's everyone doing? We're basically going to spend a couple days doing chapter 10, and then we're going to go back and hit trigonometry pretty hard. So we're going to go back to section 9.6. So chapter 10 is about polygons, and a polygon, the word polygon comes from a Greek word, and the word, it breaks down into poly, which is many, and gon, which is angles. And a polygon is basically it's a two-dimensional shape made up of straight lines, and the shape is closed. So something like that would not be a polygon because it's not closed, and nor would something like that not be a polygon because it's got a curved side. We are going to be doing everything that is doing convex polygons as opposed to something like this where the indent goes inward. That would be a concave polygon. But we're going to be doing in this chapter with convex polygons. Also, one last thing here is that a regular polygon is a polygon, and we've done some stuff already with regular polygons. A square would be a regular polygon. An equilateral triangle would be a polygon. So anything that has equal angles and equal sides is a regular polygon. Here's the word puzzle. I'll let you kind of chew on that a little bit. The first thing we're going to do here is just quickly go through the different names of polygons. There's a number of sides. So three-sided, of course, is a triangle. Four-sided is a quadrilateral, which we did a whole chapter on. Five-sided is a pentagon. Six-sided is a hexagon. Seven-sided polygon is a heptagon or a septagon. Most of the time, people call it a heptagon. An eight-sided is going to be, of course, an octagon. 9 is nonagon. 10 is decagon. 12 is dodecagon. And a 15 is going to be a pentadecagon. Something like a 27-sided polygon would be a 27gon. At least we're going to call it that. Okay, there's a couple of formulas here that I'm going to kind of quickly talk about, just informationally. How do we find the interior angles, the sum of the interior angles of a polygon? Well, we know that a triangle has 180 degrees, right? And we know that a quadrilateral has 360 degrees. And so a pentagon, I could break it up into three different triangles. And so like this angle plus 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 this angle, all these angles in these triangles all added up will give you the interior angles, some of the interior angles of a pentagon. So if I take 1, 2, 3 times 180 degrees, I should get 540, which is the sum of the measures of the interior angles of a pentagon. And the same thing with the hexagon. If I, from one vertex, draw in these triangles, you can see now you have 1, 2, 3, 4 triangles. And if I had a heptagon 7-sided, I could draw 5 triangles and so on and so forth. Ultimately, you're going to end up with n minus 2. So the number of sides is your n minus 2 times 180 degrees is equal to the sum of the interior angles for a polygon. So that's the general formula that you'll need to know for that. For exterior angles, if I have a triangle, let's say I have an equilateral triangle, this exterior angle, 1 per vertex, So if I add these three up together, well, if I had an exterior, an equilateral triangle, it'd be 60, 60, and 60, which means each of these are supplements, which is 120 degrees, 120 degree, and 120 degrees. So that adds up to 360 degrees. And if I have a square, same type of thing, one exterior angle here, 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 and here per vertex. So that each of these is 90. The supplements of those would be 90. So 90 times 4 is also 360. And what you're going to find out is no matter what number of sides we have for the polygon, the sum of the exterior angles is always going to be 360 degrees. And then the last formula in this section is the number of diagonals that can be drawn within a polygon. So if I have a polygon here, let's take a look at this pentagon. I can draw one diagonal, two diagonals, and then that's all I can draw from that diagonal, from that vertex. Then from this one I can draw 3, 4, then from this one 5, and if you notice, we already drew this one, so I can't count that again. So I can end up with 1, 2, 3, 4, 5 diagonals. Okay, and it's going to end up being this formula right here. The number of diagonals is equal to the number of sides times the number of sides minus 3 divided by 2. And the reason why is from each vertex, if you count, it's going to be n number of vertices. You can't draw a diagonal to the ones next to it. So you can't draw it this way, can't draw it this way, and you can't draw it to yourself. So that's why it's down here, n minus 3. And it's going to be n times, okay, the number of these, n is the number of vertices, and you can draw n minus 3 diagonals from each vertex. But if you notice, like we saw before, you draw it one direction, but you don't want to draw it coming back and count it twice. So that's why we have to divide it by 2. If you didn't quite understand what I just said there, it's okay, not a big deal. But I just wanted to give you some idea of why this formula is what it is. Okay, let's talk a little bit about how to use these formulas. So if I want to find the name of a polygon with 35 diagonals, I'm going to use the diagonal formula up here. So it's going to be 35 equals n times n minus 3 divided by 2. Multiply both sides by 2, so I get 70 equals n times n minus 3. Distribute the n. I get n squared minus 3n equals 70. Bring everything over to the same side, n squared minus 3n minus 70. 0 equals, and then I can factor this thing into n minus 10, n plus 7. So n is equal to 10 or negative 7. I can't have a negative number of sides, so n is going to be equal to 10. And then for number 3 here, I'm going to skip over to number 3. How many sides does a polygon have if the sum of the interior angles is 1440? Using the sum of the interior angles formula, n minus 2 times 180. It's going to be 1440 equals, and then distribute the 180. 180, or actually what I could do here is n minus 2 times 180. Just divide both sides by 180. And then whatever, let's see, that's going to come out to plus 2, 8 equals n minus 2. And then add 2 to both sides, so n is equal to 10. So it's a decagon. And then if I, let's see, let's jump down. Some of these are pretty easy. Like the sum of the measures, like number 4 here, sum of the measures of an exterior angles for a pentadecagon. And we know that no matter what, it's always going to be 360 degrees. Number 6 here, 2 consecutive angles of a hexagon are right angles. So that's going to be 180 degrees there. And for a hexagon, we know that it's going to be sum of the interior angles equals n minus 2 times 180. So it's going to be 6 minus 2, or 4 times 180 degrees, which is just going to be 720 degrees. So if I say take 720 degrees, which is total for the hexagon, and I subtract these 2 angles, 180 degrees there, I'm going to get 540 degrees, and I know that the remaining 4 angles are congruent to each other, so I just divide that by 4, and I get 135 degrees for each measure of the non-right angles of a hexagon. And then let's do one last problem down at the bottom here. Measure of one interior angle of a regular polygon. So a regular polygon is all the sides are going to be the same. And there's a couple of different ways we could do this. We can do something like this. I'm not sure how many sides it has, but I know that the interior angle is 165, so I know that the exterior angle has to be supplementary to it, so it's 15 degrees. And so I can take 360 degrees because I know that each of the exterior angles is going to be the same. Take 360 divided by 15 because each of them is 15, and that's going to give me 24 sides for the polygon. And I think that's it. There's another way to do that one, but it's a lot harder. So I'll stick with the easy way to do that problem. Okay, that's it for section 1. Section 2 is, the nice thing is basically the same as section 1. It's just more problems with regular polygons. So it's basically the same stuff. All right, that's it. Take care.